again, as usual, the previous year exam, right, is in the blackboard, right? Again, formula sheet is in the blackboard. Again, the format of the exam will be exactly the same: 5 multiple choice questions, and then 3 big problems, right? Yeah, and again, so whenever you feel like you want to go somewhere, just go, right? If you want to go home, also you can go home, no troubles, right? If you feel like you want to go somewhere, sit somewhere else, also feel free, yeah.
Would you say that the difficulty is the same level as last year?
The level of the exam?
Yeah, like the difficulty?
I usually try to keep the level of difficulty at the same level all the time, right? But of course, it doesn't mean that the problems are going to be the same. But I keep telling you that all the problems which I offer on the exam are very, very similar to the problems which we discussed in our recitation classes or in your homeworks. You saw them in your homeworks, right? So I just want to see that you're capable of doing them by yourself without any online resources. Okay, so then let's continue. And again, if you don't understand something, right, not clear, something is not clear, tell me immediately, right? I can explain it. Right. So the review is actually very short because we haven't introduced much. What we just introduced? We introduced Newton's laws, first, second, and the third one, and out of which we use most of the time the Newton's second law, and occasionally Newton's third law. An application of that Newton's law for single object, for a couple of objects connected somehow, and then for rotational object which is spinning or circling, right? Just Newton's second law. So, but anyway, let's just quickly review major ideas which you need for this exam. All right, so first, every time, of course, you have to identify all forces acting on a system, on your object. Again, you need to remember, force was introduced to describe what? In general, philosophically. Force was introduced in physics to describe what? Interactions, right? If something interacts with something, how we model it in physics, we introduce force, right? Okay. Now let's discuss all these major forces. If you have, I don't know, ceiling, here the cord, some object, right? If there's a cord attached to the object and cord is under tension, okay, we can introduce a tension force, right? So in this case, there will be tension which acts along a cord away from the object all the time, right? And most of the time, cords are going to be massless. If a cord is massless, what does it mean? Tension is going to be exactly the same at any point of the cord, right? In all the problems which we are going to see in this class, in this course, cords are going to be massless, right? Okay, so tension, first force, which I wanted to mention, right? So tension. Okay, it's a pulling force, so it acts along a rope, away from the object, away from an object. Right. Okay, the action of the force along the cord or the rope and away from the object. Then, okay, it's a first force. Then, which one? Normal force. Normal force. Normal force again comes from an interaction. Interaction of the object with some kind of surface. Right? So if you have, of course, in the simplest case, if you have flat surface, box on top, then of course normal force is perpendicular, acting on the object, right? Away from the surface. If a surface is inclined, for example, like this, let's say, and this is our object, still perpendicular to the surface, right? Still perpendicular to the surface. If you have, for example, this situation, let's say you have a ceiling and point of the ceiling, a wall and a floor. And let's say your box is over here. So how many normal forces are there right now? Two. From each surface should come, there will be force, right? This box interacts with the wall. As a result, the wall is going to exert the force, normal force, let's label it N1. But at the same time, floor exerts a force N2. Yeah?
Why would there be force from the wall if there's an edge force that's pushing the wall against it?
We assume there is a connection, right? Yeah. There might be something, right? Or if you have, for example, this situation, let's say this is ceiling, right? And person tall enough to touch that ceiling, okay, the second hand, right? So now direction of the normal force, downward, right? Perpendicular to the surface, right? It's like if I could touch on the ceiling, there will be normal force pointing down. So in this case, there will be normal force downward. Okay, then after this, okay, let's introduce friction forces, right? Friction forces. So there are two friction forces: kinetic friction when there is a sliding of one object on top of the other one, and of course there is a static friction force when there is no slide. Okay, I like this plot, which I usually use all the time. So it's a applied force versus friction force, right? So when there is a static friction force, if you push with 5 newtons and there is no motion, it means that there is a static friction force acting in the opposite direction with exactly the same force. If you increase to 10, it gives you back 10, 15, 15, and so on. So in a static situation, this plot, straight line, right, describes this static case, right? Then, when you reach maximum possible static friction force, what's the expression for the maximum possible static friction force? It's that mu, right? Mu static times the normal force. Right. So it will be, okay, let me, F static max equals mu s times normal. Okay, it's a maximum possible static friction force. Then, if you exceed this maximum possible static friction force, static friction gives up, and the object starts sliding. Now we have kinetic friction. So kinetic friction, it's a constant force. It doesn't matter how fast you slide your object, kinetic friction is going to be exactly the same. Expression, very similar, but now we should have mu k. We should use mu sub k, which is kinetic friction coefficient. All right, so I can write, so here, F kinetic equals to mu k times m. And over here we have kinetic friction. Again, this is only correct for the maximum possible static friction force. Then, how can we find directions of these forces? Direction of the kinetic friction force. All the time opposite to the direction of motion. If you know the direction of the velocity, kinetic friction force acts in the opposite direction. Okay, maybe I should write this. No, I will probably draw. Right. So if you have let's say, a surface. This is the box, this is the surface. And let's say object moves this way, so velocity v is null. Then static or kinetic friction, of course, acts in the opposite direction. This is F, kinetic. But what about static? Let's assume that we have an inclined plane, and here is our object, which doesn't slide. So v equals to 0. How can we find direction of the static friction force? Imagine situation, what if a static friction force disappeared? Imaginary situation, what if static friction force disappeared in this case? Of course, we all know that the object would start sliding down. Static friction force acts in the opposite direction to this imaginary sliding, imaginary motion, right? Okay. Which way I draw? Okay. So this will be our F static. Imagine static friction force disappeared. It will start moving in a certain direction. Static friction force acts in the opposite direction to that direction of motion. All right. So that's our friction. And gravity, of course, everyone knows, right? I'm not going to write, of course, m times g acts all the time straight down. Right? Every time we assume that the Earth is straight underneath of the system. And after that, we introduce the most fundamental law in physics, Newton's second law. Right? So if you have some object, right, and there is a net force acting on this object of mass m, it leads to an acceleration of that object a. Right? And Newton's second law described this, right? So net force acting on the object of mass m equals to mass times acceleration, right? And most of the time, our system is either one-dimensional or two-dimensional. Of course, you can decompose this equation into two equations. Sum of the forces along x direction equals mass times acceleration in the x direction, and sum of the forces acting in the y direction, mass times acceleration in the y direction. Right. So pretty much that's what we've been using for the last 3 weeks, almost every class. Just applied Newton's second law. Right. So it must be framed. Right. Newton's third law. Let's just also mention it. Newton's third law. So if you have two objects, let's say on a surface, one object and the second object interacting, right? Which I label this as 1 and this is as 2. So of course they exert on each other forces, the same in magnitude but opposite in the directions. So this will be F from 1 on 2, and this object exerts force on this one, F to 1. And these two forces, as I said, equals in absolute value, but acts in the opposite directions. Well, absolute value F12 equals to F21. You see, these are vectors, these are magnitudes, absolute values. Okay, now, what else? We can separate Newton's first and second, the second and the third law. And after that, we started looking at rotational dynamics. Rotational dynamics. So we combine forces and rotational motion. Okay, so let me just draw some imaginary rotational motion. Oh, something like this. this is the center of a trajectory. Let's say this is our object, right, of mass m, let's say. And to describe this motion, which coordinates do we usually use? R and T, right? The most convenient, right? If the object is here, T, R. If the object here, R, T. If the object here, R, T. Again, you keep moving your coordinate system. Whenever object is, position the origin at that point, R is towards the center, tangential, usually in counterclockwise direction. Right, so this is T, and that is R. Okay, tangential velocity, direction of tangential velocity along a tangent line. Right? Let's assume it moves this way. So this is our V tangential. Okay, we can also introduce angular velocity. And most of the time, we're going to use uniform circular motion. Now, let me check if I mentioned everything. Yeah. Uniform circular motion. Most of the time, it will be this situation. Uniform means what? No. Constant absolute value, magnitude of tangential velocity is constant. So your first answer was correct, right? So speed of the object is the same. So it circles at the same rate. Right? Again, it's absolute value of V tangential equals to constant. V tangential equals constant. As a result, you started saying about acceleration. So what about tangential acceleration in this case? 0, right? Because tangential acceleration describes how fast magnitude of this velocity changes. Okay, I can draw something like that. A tangential equals 0. But what about centripetal acceleration? Of course, it cannot be 0, right? It cannot be 0 because we have circular motion. If there is a circular motion, there must be a non-zero centripetal acceleration. And the expression square of the tangential velocity divided by the radius. Let's assume that this trajectory has a radius r small. Okay, centripetal acceleration. Let me write this down because we use it a lot. Centripetal acceleration. Right? Direction towards the center all the time. Towards the center all the time. You just need to remember that. Okay, let me show this. So this will be a sub r direction. Then, yeah, that's what I was planning to tell. And now, if we want to apply Newton's second law, right, to describe this motion, in order to describe this motion, we apply Newton's second law. And most of the time, we apply Newton's second law in the radial direction, because usually there is no forces in the tangential direction in our problem. So, and then, and then Newton's second law in r direction. Right. So sum of the forces in the radial direction equals mass times centripetal acceleration. This direction of this net force. What is the direction of this net force? All the time. It must be towards the center, right? Because centripetal acceleration, if centripetal acceleration towards the center, then the net force which produces that centripetal acceleration must be also towards the center, because mass is positive. Mass cannot be negative, right? So this will be our net force in the radial direction, which we can call centripetal force, blah, blah. But I usually prefer to use real names. Normal force, tension, gravitational force, and so on. Then, let's recall also very quickly rotational kinematics. This rotational motion can be described by two sets of parameters. You remember a few weeks ago, angular, right, and linear, right, and they're connected in this way, right. So arc length along this circle equals to r times theta. Theta is in radians. Basically, that is the definition of angle in radians. We use that in the our first midterm exam, right? Then, how can we connect tangential velocity with angular velocity? Through the radius again. So that's radius, right? R omega. Because sometimes we have to find out tangential velocity, and then the problem can ask find angular velocity. If you know one, you can get immediately the second one, no troubles, right? And accelerations, tangential acceleration and angular accelerations are connected again through the same radius. Yeah?
Is there a particular measurement that omega needs to be measured? Like can it be revolution per minute?
Okay. This is basically definition of angle in radians. So this formula is only correct when angle is in radians, right? So as a result, how can we get this out of that? You just differentiate with respect to time. It means that omega must be in radians per second. Must be. Only it's only then it is correct. This formula is correct.
Thank you.
Yeah. And of course, the same here. The same with accelerations. Accelerations again must be in radians per square seconds. Right. I think that's the extent of the review. And so now let's start looking at the problem. So all the time, what we used Newton's second law. First, you need to draw a physical situation, right? Then you need to identify all forces acting on the system, on your object. Of course, introduce coordinate system, right? And then decompose all the forces along x or y direction, right? And start applying Newton's second law. And sometimes, if you need to find, for example, the travel time or velocity at a certain moment of time, what else can be used? What else can be combined in order to find that velocity, for example, travel time, position? Kinematic equations. Pretty much that's what we used for the last 2.5 weeks, for the last 3 weeks. Newton's second law, kinematic equations. Kinematic equations, Newton's second law. All right? Okay, so now let's start looking at the problems. Let's probably start with a simple elevator, right? And the idea of apparent weight. Again, it's two different things. Real weight, which is the gravitational force, and apparent weight. Apparent weight, that's what you feel. And usually you feel your weight through the normal force, right? If I'm standing right now on the floor, why I feel my weight? I will feel my weight because my nerves, my feet feel the normal force from the floor. If floor disappears, I would go down and I wouldn't feel a weight for a few seconds, right, before crashing. Right? So I would be in a weightlessness. Right? So if a question about apparent weight, it just basically means what's the normal force acting on the person. Right? Because again, I don't feel my weight directly. I feel my weight indirectly through the normal force. Right? Okay. So let's assume that there's somebody or something in the elevator. Right, okay. It's a classical problem, an elevator, and some person inside or some box inside. And let's assume that this elevator is moving down and slowing down. And slowing down. So, problem in the words, and we need to find the apparent weight. Right. Okay, maybe let's write find the apparent weight. Basically, it means finding normal force. Okay, so let me draw physical situation. Okay, elevator attached to some cord. So there is a person inside. Okay, let's make it happy. Him happy, right? And it says it moves down. So velocity is down. But what about acceleration? Directional acceleration. Up. It slows down, it means it's opposite to the direction of the velocity, right? It's like when you press the brake on the car, you still move forward, right? Velocity is still forward, but you're slowing down. It means acceleration in the opposite direction, right? It's the same story here. Okay, so as a result, I can say that acceleration is upward. Right? Okay, so now, basically, that's what is given, and now we need to introduce first step. Coordinate system. Coordinate system is a must. Never skip coordinate system. Right? If the question is about finding forces or accelerations, sometimes where you position your origin is not that important. But if the question about finding position or travel time or velocity, then position of the origin is also crucial. So, which I want to introduce y coordinate. Should I point it upward or downward? Okay, that's your opinion, right? So you have constitutional freedom to choose any coordinate system you want. Which, don't listen to them, right? Upward or downward?
Up.
Better. Up. You're still following the trend, right? Logic, why upward? Yes, the most common problem, right, when students pick, for example, coordinate system downward, then when you apply Newton's second law, your acceleration will be negative. And 95% of students usually don't write that minus. They usually forget about that minus. They will put pluses and minuses, proper pluses and minuses next to the forces, but acceleration is a big issue, right? Usually students don't do that. And in this case, we know everything about acceleration. Acceleration is given, right? Basically, acceleration is given. So again, in order to avoid making that mistake, it's better to align your coordinate system along a direction of acceleration. So, why? Okay, maybe I will write to make a positive acceleration positive. So as a result, when I need to apply Newton's second law, my right-hand side is going to be positive. Right? Okay, so next we need to identify all forces. Of course, force of gravity, I'm not asking you downward, although I saw a few times students would draw force of gravity in a strange angle. So mg. Then what else? What else? Normal force. Then let me ask you this question. There is a cord, rope, whatever, attached to the elevator. Why don't we include tension?
It's not relevant to.
Can you be more specific? Not relevant.
You don't need it to measure the weight of the person.
It's not acting on the person.
Yes. That because Newton's second law, these forces acting on this object, M, that's our object which we're trying to describe. In our case, we want to describe person. So we need to draw only forces acting on the person. This cord acts on the elevator. If the question was about feelings of the elevator, right, or whatever question, right, about the elevator, then yes, we would have to include that tension force, right? Okay, so that's why tension we don't include, right? So as a result, okay, so now we just need to apply Newton's second law in the y direction. So sum of the forces in the y direction equals mass times acceleration in the y direction. Okay, since we have only one acceleration, so let me just drop subscript y. Normal force, positive, because it acts in the positive direction, positive y direction. Gravity is negative. Again, acceleration is given. Okay, let me emphasize that A is given. Yeah?
Why is it n minus mg?
What do you suggest?
Why is it n minus mg?
No, then what do you suggest? You don't know. Okay, because I'm just trying to write all the forces acting on the person. There are two forces acting on the person, right? Normal force acts upward in the positive y direction. So it goes into the equation with plus, right? Then gravity acts downward. God created the nature this way, right? So it acts in the chosen negative y direction, right? So that's why n minus mg. So, and again, this is his feelings. This is apparent weight. So now let's just solve it for that. So n will be equal to mg plus ma. This is his weight by definition. You cannot change that. He cannot change that unless she loses weight, right? Then he changed that. Plus some additional contribution because elevator accelerates. If an elevator is stationary or moves with a constant speed, then of course this term is 0 and the person would feel just his normal weight. Right? But in this case, he feels heavier. And that's what you feel when you go from the 5th floor down to the 1st floor. At the end of the trip, you feel slightly heavier. Right? But let's assume that you didn't follow everyone's suggestions, and let's say your y-axis, let's say your y-axis is downward, for example, right? Problem is solved, right? But what if y-axis is downward? How would the equation look like? So in this case, forces, mg, positive or negative, if I pick this coordinate system? Mg. If I pick my coordinate system downward, positive. So now in this case, equation would look like mg, positive, normal force, negative, minus m, and then the left-hand side, mass times acceleration. Now acceleration would be negative because our acceleration is upward. We know, I know it's given. Let's say 2 meters per square second. And direction is upward. So in this case, we would have to write minus a. So what's the difference between this equation and this equation? It's just like multiplying by minus 1. Right? So it will be still correct equation, but again, most of the time students forget about this minus. That's why I usually recommend to use this coordinate system. We only include forces acting directly on the person, on the object which you're trying to describe. So all these forces acting on this mass directly. Or gravitational force, of course, distant force, right? So again, presence of the tension will go on the person, will affect the motion of the person through the normal force. All right, now, okay, let's, no, this one. Okay, actually this is problem from the recitation classes, but in my recitation classes I usually never manage to get to this problem. I don't know if your instructors discuss this problem. Where is it? Oh, here. The problem is about this. We have a box. Okay, let's position this way. Right. And I want to apply a force, and I want to find the value of the force which I apply which I have to apply, so that I can slide it down with the constant speed. Mass of the box is given, so we need to find the value of the force that I have to apply at 45 degrees so that the object slides down with a constant velocity. Okay, let's just let's just discuss this. Erase up to this point. And actually it's a problem, yeah, it's a problem from the book, 656. 656, so it's a box against a wall. Mass of the box, I think, is given. Yeah. Mass is 2 kilograms. And I will probably start with a picture. So let's say this is the wall. Then this is my box against the wall. And it will be moving, of course, downward with velocity, which is going to be constant because we want to achieve the constant speed. Maybe I will write down first what needs to be found. So we need to find F, which way I wrote? F, so that Vy equals constant. So where is that force? I'm going to apply it at 45 degrees over here. So that's my force, and this is theta, and that theta is 45 degrees. Theta is 45 degrees. Then, another important parameter. There is a friction between the wall and the box. Kinetic friction. So, coefficient of kinetic friction is given. Mu sub k, what's the number? 0.2. Okay, so after this, we can start discussing. So, ideologically, it's straightforward. We have an object. We want to describe that object. Actually, yeah, we want to achieve this, right? So we just need to apply Newton's second law, and then along the x and y direction, and then we will see how can we get this force. Don't try to find the force immediately, somehow envision it. There is a well-developed procedure. It's a model, right? That's how we model the nature. Introduce coordinate system, draw all the forces, and apply Newton's second law. Once you apply Newton's second law, you will get two equations which needs to be solved for whatever needs to be solved. Okay, coordinate system. In this case, it's obvious. One axis horizontal, one axis is vertical. This will be my x. Y-axis, I pick y upward. In this case, there are no any advantages of picking it upward or downward. Why? Because there's no acceleration, right? In this case, I don't know, my mind a compulsion, I picked it upward. Right? Okay, after this, all the forces acting. Okay, first force, any force.
Gravity.
You pick just gravity. Usually students start from gravity, right? Everyone's favorite force. mg. Then, what else?
Normal force.
Normal force. Direction of the normal force. Away from the surface, right? Acting on the object. So in this case, normal force is to the right, to your right. Right? Okay, so that will be the normal force. Then, what's next? What's next? Of course friction, direction of the friction force. Where is it? Where is it? Here. First of all, which friction we're going to deal with? It's going to move with constant speed, right? So it's a kinetic friction. All the time, direction of the kinetic friction, direction of the kinetic force, kinetic friction force, opposite to the direction of the velocity. Okay, so it means that kinetic friction force acts upward. Fk. Okay, anything else? Just look around. Again, every force must come from some interaction. Gravity interaction with the Earth. Then on this side there is nothing. Over here there is nothing. Object doesn't interact with anything. Here nothing. On this side we have a surface. And we can get two forces from the surface. Normal force and the friction if the surface is rough. Okay, two forces, normal and kinetic friction. Nothing else. Okay, and after this, let's just start applying Newton's second law. Which direction should I start revealing first? X or Y direction? Actually, it's nothing wrong with starting with either of these directions, but in order to have a nice flow of the solution, you think Y direction. Why?
Well, you can get kinetic friction because the net force in the Y is 0.
Is it a Y or which direction? Look carefully. You're saying that we will have to deal with the kinetic friction, right? And kinetic friction is equals to, where is it? Mu Kn. But normal force acts in which direction?
Sorry.
X, right? So it's better to start with the X direction so that we can find the value of the normal force. Then the value of the normal force will be used to find the value, the expression for the kinetic friction. And we will be able to write the equation in the Y direction. Right? Yeah?
Is there anything wrong going the other way?
No,
Using
nothing.
friction force?
But of course, at some point you will realize that you will have to stop, move to that direction, find that the value of the normal force, kinetic friction, and then you have to go back to your original direction. Right? No, nothing wrong. But as I said, in order to have a nice flow of the solution, I usually start with the direction to find the normal force. With that direction, which allows me to find the normal force. Right, so as a result, X. First, I will start with the X direction. Let me check if I mentioned everything which I was planning to mention. Yep. Okay, actually, usually, first I prefer to find, you know what, let me erase this because this E constant is on my, I need that space. Right. Let's just decompose this force, right, first before we start writing down the equations. Let's decompose F. Right. So this will be what? X direction, I mean X component of the force. Doesn't look good. Okay. This will be the Fx, right? So it will be F times, we need to find adjacent side, cosine of angle, cosine theta, right? It's F times cosine theta. Then Y component, you know what, now I don't like that this is in Y way. Okay, this will be Y component of the force, right? If we use cosine here, there must be, sine must be used here. F sub Y equals F times sine theta. Okay, now, once I have these components, I can start writing down the equations, right? Sum of all forces acting in the X direction equals 2 mass times acceleration in the X direction. Universal law applied in this direction. What's the value of acceleration in the X direction? 0, because object, we know we observe object that will be just sliding down in the vertical direction. So there is no motion in the x direction, right? No motion in the x direction, it means acceleration is 0. So we just apply what we observe. Okay, so let me dump this. No motion in x direction. Right? That's why it is 0, because there is no motion. We observe it, and we apply what we observe to our. Because if we don't apply this, we will never be able to find the normal force. We need to apply something. So from here, of course, we can write this down explicitly. So all the forces in the x direction, normal force, positive or negative? Of course positive, because I pick my x-axis that way. So normal force positive. Then what else acts in the x direction? F cosine, positive or negative? Negative, of course, because this force acts in the negative x direction. You see this force. So it's minus f cosine theta equals to 0, right? Because acceleration is 0. So all this force, there are only two forces, right? Normal force and this component of applied force on my finger's force. Right, so of course this allows us to find the value of the normal force. It will be F cosine of angle. So forces, this is not known, but that's how it is going to, so right now it's just unknown. It's just unknown. Right? When we write down the equation in the y direction, we should be able to find this value. But for now, we just drag it as a symbol. So then, as a result, can we find kinetic friction force? Now. Yes, now we can find kinetic friction force, mu k times n. That's why I started with the x direction, so I can find kinetic friction force, which I need to write down Newton's second law in the y direction. That's the reason why I started with the x direction. And so now as a result, F kinetic equals to mu k times n. Mu k times this mu sub k n, wait, not n, times F times cosine of angle. Okay, so we prepare this ingredient for the equation in the y direction. Right? So that was x, and now y. So sum of the forces, y components, sum of the components, y components of all forces equals to mass times acceleration in the y direction. Again, just application of the universal law. What's the acceleration in the y direction? 0? Yeah, because that's what we want, right? We want to move the box with constant velocity in the y direction, right? So since we want to have constant velocity, so that's what we want. Acceleration must be 0. We want v sub y be constant. That's why it is 0. Okay, and so now let's just write down explicitly all the forces, y components of all forces. Kinetic, positive or negative? Positive, because it acts in the positive y direction. So F sub k, positive. Then gravity, negative, right? Minus mg. And this component of the force, positive or negative? Huh?
Positive.
Positive or negative? Yeah, because when okay, you started shaking your head, right? So since it acts in the positive y direction, so it's positive, right? Fy So it's plus F sine theta, right? Is that all? Yep. I don't see anything else. Okay. It is equal to 0, right? So explicit form of the Newton's second law in the y direction. So now we just need to take our friction force and plug it over here. Right? Again, that's why I started with the x direction, so I can find friction force, so I can use it in our y direction. Okay, I don't want to go lower, right? Because it will be difficult for you to see. Okay, let me separate it this way. And so now, let's plug it. You know what, I'm afraid that, let me move this way. So, kinetic, mu k f cosine theta. I'm just rewriting this equation with this kinetic friction force. Minus mg, then plus f sine theta equals 0. Right? How many unknowns are there in this equation? F. One equation, one unknown, okay? So there's only this F. So this is our unknown. The rest is given. So let's just solve it for F. This mg goes to that side. Here I will factor out F. So it will be mk cosine theta plus sine theta equals to m times g. And so from here, F equals to weight, force of gravity, divided by mu k cosine theta plus sine theta. So let me check if I ended up where it was supposed. Yeah. So everything is given mass, given this is acceleration due to gravity, given. So you can plug, calculate, and you will get 23 newtons. In this case, it's a little bit kind of bulky, maybe a little bit tedious, but strategy is exactly the same. Draw a system, introduce coordinate system, you have a freedom, but of course be smart and pick the best coordinate system to reduce chances of making a mistake. Identify all the forces, and now everything is in front of you, and now you just need to transpose, just move all the stuff from the picture into your equations, into your Newton's second law equations. That's it. And then you will have a couple of equations which needs to be solved for whatever needs to be solved. Okay. Any questions? Okay, so I will erase this now. Can I erase this, please? Okay, this problem is without number. I don't remember where I took this problem. So, a child sliding down it's not the most horrible problem. I remember when I picked this course up from the previous instructor, and I used some of his previous exam materials, right, as an examples, right, and there was a problem. So there is a merry-go-round with a child, right, spinning with a certain angular velocity, blah, 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 blah. And then here comes a bullet of 2 kilograms. I was stunned. So peaceful, such a peaceful beginning, right? This merry-go-round, right, child And here comes the bullet, right? Not into the colliding with the merry-go-round, right? With the disk basically, right? And then you have to find some changes in the velocity, right? Changes in the amplitude of screaming, right? So it's a very nice problem. This is a very nice problem. All right, okay. Okay, so let me draw the picture. Right, nice, smooth. Right, so this is horizontal. Okay, angle of inclination immediately before I forget it. Theta is 34 degrees. It's not that steep. The total length of the incline, let me label it as L, 10 meters. Okay, from this point to that point. Coefficient of, there is a friction, so coefficient of kinetic friction, right? Mu sub k. Mu sub k is 0.51, but you know it's kind of rough. 0.5, it's not that small, right? Coefficient. Then you're not going to push this child. At the very beginning, it starts from rest. Starts from rest. Peaceful beginning, right? V naught equals to 0. So what we need to find, okay, so let's say this is our initial point, right? So it starts from this point and it ends over here, right? Final point. So we just need to find the velocity at the final point. So what we need to find, VF, final velocity. Okay, let me check if I give you everything. Yeah. Hello. You can come closer instead of waving from the back. Okay, so we need to find what? Velocity. One of the kinematic parameters, right? One of the kinematic parameters. Immediately, it means how many equations or laws we're going to use. Just first, I want to discuss general strategy. Like before a battle, generals will get together and decide we're going to do this way, we're going to move that way, right? So we need to find one of the kinematic parameters. Immediately, it means what we will have to use? One of the kinematic equations. One of the kinematic equations, right? But before we start using kinematic equations, of course, first we need to get to the world of kinematics. Usually I draw this sort of diagram, right? So here we have a world of forces, right? And here we have a world of kinematics. Kinematics, right? And in order to get to the world of kinematics, which is what? X, position, velocity, acceleration, time, right? Newton's second law allows us to get to the world of kinematics to the point of acceleration, right? So this is F equals ma, right? So we have a bunch of forces, right? System. So we're going to apply Newton's second law to get to this acceleration. And then once you're there, you can use kinematic equations to find velocity at any moment of time, at any point, right? You can find position if you want. You can find travel times, again, now using kinematic equations once you are in the world of kinematics, right? But before, in order to get to that world of kinematics, you need to apply Newton's second law, right? So in this case, just 2 steps, okay, big steps, reasonably big. Newton's second law, find acceleration, and then kinematic equations to find whatever you need to find in the world of kinematics. Okay, maybe even like this. So first, Newton's second law to get to the acceleration, and then one of the kinematic equations to get to the velocity. So, block diagram of the problem. Okay, let me finally erase all these residues. Right, okay, so now let's get into the details. Of course, first of all, I need to draw an object, right? Child, not an object, right? So let's say this is, okay, it looks like a big fit child, right? Okay, happy face, right? And support it. And after that, coordinate system. Again, you can pick any coordinate system, right? You can pick x-axis this way, y-axis that way, but it's not the most convenient, not the most, not the most convenient coordinate system, right? In order to reduce the algebra, right? In order to simplify algebra, it's better to pick y-axis perpendicular to the incline, right? And x-axis along the incline. And you see, I position the origin in this point. In this problem, position of the origin is very important. Because then we will have to mess with these kinematic equations. And the kinematic equations, of course, they're sensitive to where the origin is. In all the previous problems, I never emphasized where was the origin. Because it wasn't that big deal. We just wanted to know positive and negative directions. But here, okay, origin is very important. And after this, all the forces, right? Normal force, perpendicular to the surface. Okay, let me step away. I don't want to ruin this picture of the child. I don't want to stick the normal force through the child. Then, okay, friction force. I forgot who I was asking, right? Friction force, direction of the friction force, up the incline, because the velocity is downward, down the incline. So this is F kinetic. Again, the reason is because it's sliding down, so velocity is down. And, of course, ubiquitous gravity, mg. On purpose, I usually just draw it to this bottom line in order to then have nice triangles in order to discuss angles. Anything else? That's it. Child interacts with the Earth. It interacts with the surface. Surface gives us two forces, normal force and friction force. That's it. There are no any other interactions. And so after this, okay, we have all the preliminary steps, all the ingredients are here in front of us, so we just need to start applying Newton's second law. Except, before I start applying Newton's second law, we need to decompose all the forces, right? Let's do that final step. Normal force, total purely in the y direction, no troubles. F, friction, also purely in the x direction. Gravity needs to be decomposed. Let's do that, and then we will start writing down the equations. Okay, so this is the y direction. Right? So in order to find y component, I just need to draw a normal line perpendicular to the y direction. So as a result, maybe I use blue, right? So this will be my mg y component. Okay, again, for most of you probably you even remember by heart what's the value of this angle, but still I see plenty of students make these mistakes, right? How I usually find what's the value of this angle. So this angle is, look at this triangle, this point, this point, this point. It's a right triangle, right? It's a right triangle. So if this is angle theta, this is 90 degrees, so this is 90 minus theta. All the time play with right triangles. And then this angle and this angle, they complement each other to 90 degrees. So that's why I usually draw mg to the bottom, so I have nice triangles. And as a result, this is theta. It's very simple, simple geometry. So as a result, y component mg times which function? Sine or cosine? Adjacent side. You see, we want to find the side which is adjacent to the angle. Adjacent, neighborly, close, right? Cozy, cosine. Right. Weird, yeah, I know. But as long as it works. Cosine function, guys. If you are not confident, right, at the end of the exam, or at the end of the formula sheet, there is a triangle with the angle, and you can see cosine or sine function. Check that quick. If you're not completely confident. Right, so then this, okay, and then that what? The x direction. So this will be our mg x component. Now, of course, it is sine mg times sine theta. Okay, so now everything is on the board. So we just need to start applying Newton's second law. Now, which direction? Again, it's not a big deal, right? You can start with any direction, right? And you will be able to solve it. But again, in order to have a nice flow of the solution, right? Instead of jumping up and down, right, from equation to the equation, it's better to start with this. With which direction? Yeah, you need to, we need to find normal force in order to write down the expression for the friction force. Friction force in the x direction, but the normal force in the y direction. So in this case, it's better. Again, it's not a mistake, right? It's not a mistake, but of course, it's better to start with the y direction. So it will give us a normal force, and then you will be able to find friction force, which you need for the x. Okay, so that's the logic. So let's start with the y direction. So sum of the forces in the y direction equals mass times acceleration in the y direction. Acceleration in the y direction. Yeah, we need to apply that information. We know that the object is going to slide down the incline. So we have to use that piece of information, otherwise we will never be able to find normal force. So we need to dump this acceleration. No motion in y direction, in the y direction. Okay, so as a result, now we can write down that the normal force positive minus mg cosine theta equals 0. So of course from here, n equals mg cosine theta. It's basically a quiz which you had yesterday and the day before yesterday, right? Exactly the same. Okay, not exactly, very, very similar. And so as a result, it allows us to find kinetic friction. Right? Formula on the formula sheet is given, will be given. Here it's a mu k times n. Mu k times n. Mu k times n. U sub k mg cosine theta. Good? Okay. All right, so now to the x direction. Component of the gravitational force, positive or negative? Just to keep you awake. Component of the gravitational force, positive or negative? Component, this component. You see, you need to look. That's why we introduce coordinate systems, so we know which direction is positive and which direction is negative. X is down the incline. It's the direction of x component of the force, so you don't have to guess. Everything is in front of you if you drew the picture. If you draw the picture, right? You just need to transport all these into the equations. Right? Okay, so positive. So it will be Okay, now let me write first universal stuff, right? Fx equals to ma. Okay, I will drop subscript a. I mean x subscript x. Right. So what? Mg sine theta. Okay, I will emphasize positive plus. What else acts in the x direction? Friction force, negative, right?
Yeah.
Yeah, minus. So minus Fk. And anything else? No, that's it, right? That's it. There are only two forces. And it is equal to mass times acceleration. Okay, so now let's plug our friction force, expression for the friction force, mg sine theta minus mu k mg cosine theta. In this physics 1 class, this g is almost everywhere, and I remember for first couple of years, every time you pronounce g, and then j starts appearing. And then at the end of the semester, in the evaluation, students wrote something like this, right? J. Now I try to control myself usually, right? But sometimes still feel like saying that. All right, so Ma. So now, mass distraction, right? All the masses will be canceled. M. And we're getting acceleration. So as a result, acceleration equal, and I will factor out g sine theta minus mu k cosine theta. Okay. So everything is given. Angle, coefficient, g. So if you plug numbers, you will get 1.37 meters per square second. It's not the acceleration for screaming like in a roller coaster. It's kind of boring acceleration on 1.3. So now, basically at this point, we've come to this place. And now it's a question of kinematic equations. Is it allowed, are we allowed to use kinematic equations? Why? Yeah, we do have acceleration, right? So why not? But it's not enough. What's wrong or what's so good about acceleration? When can we use kinematic equations in general? You know that. When acceleration is, okay, gentlemen, acceleration is constant, right? Only in that case we can use kinematic equations, right? Otherwise, if acceleration is not constant, then you just need to just integrate Newton's second law. But it's slightly ahead of us. So now, okay, maybe I'll just move slightly, turn the camera slightly, because I'm afraid that that side is not a little bit full. Okay, so now, since A is constant, we can use kinematic equations. So which kinematic equation is the best one in this case, or the most convenient? Yeah, the no time equation, right? Because again, the question is not about finding time. Time is not given in the problem, so it's a clear indication that the equation number 3 will be probably the most convenient. So equation 3, so which is square of the final velocity equals to the square of the initial velocity plus 2a x minus x naught. here we use all the time kinematic equations, but in the upper undergraduate level theoretical class, classical mechanics, I usually not forbid students from using them. I just usually force them to integrate Newton's second law, integrate the second order differential equation. Right, so now let's simplify. Initial velocity was, okay, it sounds so horrible, the child was released, right? But it was, she was, right? Then initial position, 0, because I position my origin there, right? 0. And the final coordinate is L, 10 meters, right? The final coordinate is 10 meters. So that is 10 meters. Acceleration we just found, okay? One unknown velocity, so we can easily define it. So V final equals to square root of 2ax. So if you plug it, you will get 5.2, okay, with 3 suffix meters per second. Okay, so now two objects. Complexity goes up. There's so much wires around. Right. So two blocks. So now we have two blocks. Oops. M1 is, I think it's M1, 4 kilograms, and M2 is 5K. Okay, not important. I want to draw the picture. Incline, then down. Right, so first block is here, and this is M1. Then there is a pulley, so that is a pulley. As usual, we're going to assume that pulley is massless and frictionless, right? If the pulley is massless and frictionless, what does the pulley do in the problem? Not much, but just redirect the tension, right? So first it will be, the tension will be acting this way, right? And then tension in the port. And then it will be vertical. So this is the cord, and here we have a second object. So let's call it M2. Okay? Right, so what else is given? Oh, there is a friction in the incline. Okay, so there is a friction. There is a friction. So coefficient of kinetic friction is, I don't remember, 0.15. 0.15. What else? The angle, theta. All right. 30 degrees. Okay, so what we need to find? We'll need to find the acceleration and the tension. Okay, so now we have two objects, not just one object, right? So we want to describe, basically our system is two objects. And these two objects move not in the same direction. They move in the opposite, not opposite, different directions. They move in different directions. So as a result, in this case, it's better to use two different coordinate systems. It's not a crime. Still, you will get the normal equations, right, which will be connected to the magnitudes of the tension and acceleration. Okay, so one coordinate system for this object. Standard, classical, right, x-axis along the incline, y-axis perpendicular. Right? So which y-axis is, x-axis this way, y-axis is that way. And for this object, which way I picked y-axis this way. Probably I should have started with different word, not coordinate system. Just now I realized. Can you tell me what is a direction of acceleration? Can you? Kind of challenging, right? Because there is a friction, right? The masses are kind of close to each other, right? Maybe even that block can drag the whole system in a counterclockwise direction, or maybe in a clockwise direction. I probably would never bet my money on this, right? So it's difficult to tell what will be the direction of acceleration. So in these cases, let's just assume a certain direction of acceleration. I told you already we used that a couple of classes ago in the lecture, right? And we're going to use this trick in physics too quite often. Right? So let's assume a direction of acceleration, solve the problem, and if your acceleration happens at the end negative, okay, so what a big deal, right? It means just opposite direction, right? Because in this case, yeah, I cannot tell what will be the direction of acceleration. So we'll assume that this box drags the whole system. So I will assume that this is my acceleration. I assume. Okay, I assume. Right? And then, of course, this object will be accelerating also that way. After this point, I should have started choosing the coordinate system. Right? Just realized after. Right. Okay. And now, all the forces. We need to identify all forces acting on the objects. Okay, let me start with this one. I'm not asking you. M2G. We need to be careful and keep track of the subscript, because again, subscripts, again, I see quite often in the solutions it's a mess. M, M1, M2, or somewhere it's M and then it disappears, right? It's, as a result, it's total mess. Right? Carefully. Then tension away from the object along the cord, right? Along this rope. So tension. Then, now let's identify all forces acting on M1. Any force on M1? Normal force perpendicular, right? Of course, perpendicular. Normal force, M. Then, what else? Gravity. You pick the easiest one. Right, no, it's M. Okay. I was warning you, and I did that, not mistake. Of course, I will realize sooner or later. What is missing?
Subscript.
Subscript. Subscript. All right, so it will be M1G. And we need your expertise in the direction of normal, in the direction of friction forces. Hello? Yeah. We need your expertise in the direction of the friction force. Down the incline, right? Down the incline, right? Down the incline. I assume that actually it moves that way in acceleration that way. Right, so, as a result, this will be my Fk. Okay, so now that's the whole story. And again, before we start writing down Newton's second law, we need to do what? Small piece? What, tension?
Yeah.
Oh, yeah.
On M1. Yeah.
Okay, good, good, good. Right. Yeah. Tension, right? Right? On M1. Where's tension? Right. And magnitude of this tension and that tension the same because we assume that pulley is, maybe I will emphasize, massless and frictionless. Massless and frictionless. If a pulley is massless and frictionless, it doesn't change the tension in the cord. But again, maybe like in a month or month and a half, we will start looking at the cases where pulley is not massless and the tension will be different here and here, but not now. For now, tension is the same. Right, and so now again, let's decompose all the forces along x and y directions. So no troubles except for mg. Right, so let's just decompose mg. Okay, I will use probably blue. Right. So this will be our y component. This will be our x component. What's the value of this angle? What's the value of that angle? It's theta, 30. Yeah. So again, the same arguments. First this triangle, this will be 90 minus theta, and then it complements to 90 degrees, that's theta. And so this component, y component of the gravitational force, I forgot. Okay, anyway, so
mg sine theta.
again, look, relative to this angle, we're trying to find which side.
Cosine theta.
We're trying to find adjacent side. Adjacent side, again, adjacent, neighbor, friendly, cozy, right? Cosine.
Yeah.
Stop laughing. Don't tell to anyone, right? Of course, it's not my way of remembering. It's just down into my blood, right? Cosine and sine function. Right, so it will be mg cosine theta. And x component, obviously, then mg sine theta. Mg sine theta. Okay, now we're ready to start writing down the equations. Probably I will start first with M2 because the easiest, right? I will just write down the equation for the second mass and then I will start taking care of that mass. So now application of Newton's second law. In this case, do we need kinematic equations? No, we just need to find acceleration force, one of the forces. Newton's second law will take care of that, right? So let me start with M2. Again, if something not clear in terms of my handwriting, tell me immediately, right? Because students complain that it's impossible to tell the difference between N and U, for example. Okay, so what? Gravity, positive. We're looking at this y-axis, right? So M2G positive. M2G positive. Tension is negative, again, relative to this coordinate system, relative to this coordinate. So minus T equals to M2, and acceleration, I assume, is in clockwise direction. That's my positive y direction. M2A. Agree with this equation? Okay, awesome. Now, so that will be my equation number one. How many unknowns do we have in this equation? Two unknowns, so pretty much it means it's not self-consistent. We need to add a second equation, right? So that's why I put one, and now let's start searching for the second equation. So of course now let's look at object M1. And now we have two directions, x and y. And since there is a friction force, we have to start not we have to, it's better to start with the right direction, right? In order to find normal force, which allows us to find the friction force, which can be used, which will be used later to write down Newton's second law in the x direction. So, y. So m1, and let's start with the y direction. N is positive. Now we're looking at this coordinate system, y upward, so n is positive, and gravity negative minus mg cosine theta minus m. And again, I did the same thing. Subscripts. I warned you, and I'm making the same thing. But sooner or later, of course, I will realize, right? So whereas it's m1, right? m1, m1. Right, so minus m1 g cosine theta, and that's it, equals 0. Again, acceleration in the y direction is 0 because we know the object is going to slide along the incline. So we need to use that, otherwise we will never be able to find the normal force. Right, so n equals to mg cosine m1 and so, as a result, kinetic friction, mu k times n, so it will be mu sub k, m1 g, k. Finally, I did not forget about the subscript. And now we have all the pieces, all the ingredients to mess with the x component of the Newton's second law, right? Tension, positive or negative? Okay, anyway, all right. Tension, positive? Yeah, because it acts in the positive x direction, positive x direction, up the incline, so tension positive, kinetic friction negative, and the coefficient of component of the gravitational force is also negative, right, because it acts in the negative x direction. Right. Okay, let me write. So first we have x, ma. And you see, I did not put any subscript next to acceleration because these two objects are connected by stretched cord, so acceleration is going to be the same. Right, so t minus fk minus m1 g sine theta equals to m1 times acceleration. And again, here subscript 1. Right. Okay, so now let's plug friction force. And we're almost there. So this is the stuff from the previous problem. Let's just erase this. Or maybe I will make one more, use one more line here, right? T minus mu k m1 g sine theta, cosine theta, right? It's a friction, and minus m1 g sine theta equals m1 times acceleration. Don't even think about canceling mass right now, right? You cannot, because I've seen just recently, right? One student just canceled masses over there, but there is no m next to tension, so you cannot cancel it. So you need to keep all the masses. So again, how many unknowns? T and acceleration. So this equation plus this equation, two unknowns, two equations, physics is over. Now we just need to solve a system of two algebraic equations with two unknowns. Right? How are you going to solve it? It's up to you. In this case, no, nothing. Just whatever you feel like doing, right, in terms of solving it. So, first equation, and the second equation and the first equation, right? Which way I did it? Okay, I got t from the first equation and then plug it in the second. So, from equation number one, t equals to m2g minus m2a, right? This equation. Yeah. And now plug it in the second equation, right? So the result, second equation, I can start rewriting it here, right? Okay, now we have to be careful. Right, so m2g minus m2a. So I just rewrote this instead of tension. And now the second term minus mu k m1g cosine theta minus m1g sine theta equals m1a. I hope I didn't make a mess with the subscript, I hope. I tried to be careful. Right, so now only one unknown, acceleration. Right, so where is that acceleration? It's here and here. There are two places, so now let's just combine them on that side, on the right-hand side of the equation. So now just a massaging the equation. Simple massaging, moving terms around. Right. So it will be m2g minus mu k m1g cosine theta minus m1g sine theta equals to m1 plus m2 times acceleration. Okay, so we're all set. So we'll just divide everything by m1 plus m2. m2g minus, you know, g can be factored out, right? I don't feel like doing it. Which way? Yep. I will just factor out m1g here. m1g mu k cosine theta plus sine theta divided by the total mass of the system. Yeah. So if you plug all the numbers, you will get more fun, 5.35 meters per square second, more than what we had in the previous problem. And then if you want to know tension, okay, plug it into this, and then tension can be easily found. M2g minus a, and the answer is 22.25. 22.25 newtons. So you see, it's very, very straightforward, right? It can be a little bit tedious, right, in this case at least. But exactly the same procedure, just Newton's second law. Something is not clear? No? Okay, awesome. But of course, you need to identify all the forces, because if you forget one force, yeah, it will mess the whole thing up. Comments, complaints, questions? Again, the child. Now, stop cruelty on children, right? Right. Only merry-go-round nobles, right, of 2 kilograms, right? We need to find some simple things. It's quite straightforward problem, just to refresh a few things. Right. So again, we have a child on a merry-go-round. Right. Okay, I will draw probably the picture. So we have a, basically it's a disk. And child is sitting over here, right? Let me give him 2 legs, right? Okay, happy face, mouse, right? It's called modern art, right? This is, let's say, radius, distance is 1.2 meters from the center of the merry-go-round. Right. And we know that the child, right, a child moves with what, 1.3 meters per second. Which velocity I'm talking about? 1.3 meters per second. How do we call that? What's the name of that velocity? How do we call that velocity? not you, right? It's a tangential velocity, right? There's only one linear velocity. You see the units, meters per second. It's some kind of linear velocity, right? And there is only one tangential velocity in this case, right? Of course, there's an angular velocity, but angular velocity has different units, radians, for example, per square seconds, and so on, right? So that velocity, okay, let me draw it here. So let's assume it's spinning this way with angular velocity. So the tangential velocity, it's this, okay, vt. Let me draw it as a vector, right? Okay, so now I can write that this is actually v sub t, tangential 1.3 meters per second. Okay. How can we call his motion? Of course, it's a circular motion. Which word can be added? Actually, yeah, this is, it's not an instantaneous, it's a constant speed, right? It's a constant speed, okay.
Uniform circular.
Yeah, it's a uniform circular motion. It's uniform circular motion. So we have uniform circular motion. So as a result, tangential acceleration is
Constant.
tangential acceleration. It describes how fast this tangential velocity change, magnitude of this tangential velocity changes. Does the magnitude change of velocity? No. So it means the tangential acceleration is, it's a constant, but zero, right? There is no change in the magnitude of the velocity, right? So tangential acceleration is 0. Okay, I'll just write A tangential equals 0 because it's uniform circular. But centripetal acceleration, of course, it cannot be 0 because we have circular motion. If centripetal acceleration is 0, it means there is no circular motion, right? So, so the first question is actually find that centripetal acceleration. But A sub r is not 0. Right? Again, let me emphasize that this is centripetal acceleration. Right? Okay, so let's find it. A sub r. So at this point, you just need to remember the formula for the centripetal acceleration. Or it will be given in the formula sheet, right? Where is it? I wrote it somewhere. Ah, there it is. Right. It's square of the tangential velocity divided by the radius. A sub r equals the tangential squared divided by the radius. In this case, it's not the radius of the merry-go-round of this disk. It's a distance to the child, because the child is executing this circular motion, right? Sounds again so horrible, executing circular motion. Right? Because yeah, tangential velocity depends on how far an object is from the center of rotation. Right? Okay, so in this case, r is this r capital. So it will be 1.3 meters per second squared divided by 1.2 meters. Right? And the answer is approximately 1.41 units of just regular acceleration, meters per square seconds. Again, here, not much of a conceptual analysis or anything, just I want to refresh a little bit again rotational kinematics, because as I know, the students struggle with that a lot. Okay, now, next. We need to find the net horizontal force exerted on the child. Basically, net radial force. Can you tell me immediately what will be the direction of the net radial force? Direction of the net radial force. We discussed that in the review, right? Direction of the net radial force towards the center, because we have circular motion, right? That circular motion, child executes circular motion because of net force towards the center, which we can call centripetal force, right? But which real force plays the role of this centripetal force in this case? Which real force? What? No, we're not doing anything with the rope and the child. Right? Normal force in the vertical direction, right? It will just balance your weight, right? So the child doesn't go through the merry-go-round to the ground, right? That's a normal force will take care. But which force keeps the child on a circular motion? Okay. Friction. Which friction? Static friction. Imagine. Revelation, right? Imagine a child sitting on an icy surface, right, of this merry-go-round. Once you start spinning, the child will just slide away from the fun. Maybe it's additional fun, right? But not what we want to describe, right? Static friction force. That's the name of the real force which works here as a centripetal force, as that net force in the radial direction. Right. Okay, so now let's just find it. And so, how can we find it? Net force? Huh?
That's times acceleration.
Okay, yeah. I thought you would start suggesting to use some of the formulas for this friction force, but we don't know any information, right? We don't know the static frictional, we don't know anything, right? But we know that according to the Newton's second law, sum of the forces in the radial direction equals to MAR, right? So we know acceleration we just found, multiplied by the mass of the child, which I didn't give you, right? But it's given, right? All right, M, what? Ah, no, 22, good. Because first I thought it's a 2.25 kilograms, right? 22.5, right? We're not dealing with toddlers, right? 22.5 kilograms. Okay, it sounds like a child. Okay. So it will be 22.5 kilograms times 1.41 meters per square Okay, maybe I should write. So what we need to find the net radial force. Which, of course, maybe I will just write. Which is F static. Which is the static friction force. So if you multiply it, what I'm not going to do it, you will get 31.7 approximately newtons. Now my GoPro went to sleep. At a certain point. Although it's possible maybe right now to better, we cannot go into revive it. So, next problem. Okay, any questions about this? Yeah.
How does the static force keeps it going in a circular?
Say it again.
How does the static force keep it going in a circular?
Static force going in a circular motion. No, a static force basically provides that circular motion.
Yeah. How?
How? Because there is a roughness between and the surface, right? So friction. Because of the roughness, right? I'm a little bit confused how to. Of course, the nature of friction forces are not that simple, right? The roughness is just very crude description, right? But of course, even if you polish them, then intermolecular forces will start acting. Right? Yeah.
Does the static friction force keep the kit from flying off?
Yeah, but sliding off. Otherwise, this kit will slide down this tangential, along this tangential direction.
So because
Right?
it-
It's like in the car on the road, right?
Go like this.
Yeah, of course.
That
But
was
of
his
course,
question.
friction force, this static friction force acts towards the center, right? So that is our F static, right? Right, anything else? Now, next is about object circling in a vertical direction. So now we're not going to use a child, right? So this way, right? And we will have to find something. It will be probably the last problem for today's review. Yeah.
Is the universal law of gravity going to be like that?
Yeah, why not? All right, something like satellite orbiting, but again, it's rotational dynamics, right? Except for nature of the force is different, right? So just G(m)(m) divided by square root of the distance between them, right? Right. So ball on a string. Right, let's label this problem this way. Name it. Ball on a string. Okay, our mass is given. What is mass? 1 kilogram. Okay, nice. All right. So then, radius of the circle is 1 meter. Of course, it's a vertical circle. So we have a vertical circle. Right. Okay, I will probably start with the picture because I need to see the diagram. So let's see. So center. Right. So R. I use capital. Yeah, R capital. And again, most of the time we're going to discuss the top and the bottom. Right? So we just get close to the center. So let's say this is ball at the top. This is the court or string. So we know that this speed of the ball at the top is 10 meters per second. So it's a part A. Part A, V at the top is 10 meters per second. What's the name of that what's the name of that velocity? And don't try to pass it on him, right? So what's the name of that velocity? How do we call it? He already helped you once. It's the same name.
Oh, tangential.
Tangential velocity. When we have circular motion, there's only one linear velocity in this case, right? Tangential. So I assume that it moves this way, it spins this way. It's omega, and we're talking about this V. V at the top. It's a tangential velocity. Okay, let me emphasize on that. That is tangential velocity. We need to find tension in the chord. So let's just find tension at the top. Again, these problems are very well structured. Basically, I would say straightforward. Again, just application of Newton's second law. But before we start applying Newton's second law, we need to introduce coordinate system. Which coordinate system do we usually use in the problems like this? Radial and tangential, right? In tangential, nothing usually happens in the problems like this. We usually discuss uniform or circular motion, right? Although in this case, it's difficult to achieve uniform circular motion because of the gravitational force, right? That's why we usually discuss on the top and the bottom. Right, so coordinates T and R, and now all the forces. Typical preparation for the Newton's second law, application of the Newton's second law. Tension acts which way? Huh? That? Tension is along a rope away from the object. Yeah, of course, down along the chord. Right, so that is tension. Right. Don't even thinking about adding some normal forces or thrust or something else. Right. Everything is within like 4 or 5 forces, right? It's a ratio. All right. Then what else acts? What else acts on the object? On the ball? The ball is the object which we try to describe, right? So what else?
Gravity.
Gravity, of course. And again, it's down. So 2 forces, mg. Okay, so that's the mass. Mass is given. So I can put here m. Right. Okay, so all the preliminary steps are done. All the ingredients are in front of us. Now we just need to put them all in the Newton's second law. In the radial direction, in the tangential direction, we assume that there's no acceleration. And there are no any forces. force equals 0, acceleration equals 0, uniform circular motion, blah, blah. Right, so sum of the forces in the radial direction equals mass times acceleration in the radial direction. Newton's second law in the r direction. Forces, positive or negative, both of them positive, right? Because they both act in the positive r direction. Right? So it will be t plus mg equals, and acceleration is all the time centripetal acceleration can be only towards the center, right? So, okay, let me use different. So this is a sub r. So it's positive. That's why we pick r direction towards the center to keep our acceleration positive. Right. So it will be m v top squared over which r I used r capital. How many unknowns are there? Just one. Only tension. The rest is given, right? So very, very straightforward. T equals to mg. Wait, no. Right. mv top squared over r minus mg. So if you plug these numbers, I'm not going to do it, you will get approximately 19 newtons. Yes, since I use two sig figs. Let's assume that's two sig figs. 19 newtons. It's also possible the question like this, for example, what's the value of the velocity at the top when the tension, when this string goes slack? So how can we express that in our this Newton's second law? When string goes slack, what does it mean?
T is equal to 0.
Tension disappears, right? We can have only tension force when the cord is under tension, right? If cord goes slack, okay, there wouldn't be any force acting on the object, right? So at this point, so you just need to take t, put t equals to 0, and you will be able to find that the value of the force at which cord goes slack, right? So it's basically if I don't move fast, so you see at the top it starts going, okay, that's too fast. Okay, but you see that was close, right? At the top it starts just going down, tension disappears. Okay, and the last part, let's just look at the bottom. And at the bottom, what do we have to find? Again, we just, okay, so we know that the cord maximum tension that this cord can handle is 109.8 newtons. So we just need to calculate how fast the object can move, right, to get that maximum tension. If you increase the speed, the cord can break and the object can fly. So let's just find that maximum velocity which is allowed to spin, to spin this object. Otherwise, if you exceed that maximum velocity, you can break your cord and the object flies. So part B. Okay, so let me, which way express that? Okay, T maximum is given. T maximum is 109.8 newtons. And of course, when you spin this object, the maximum tension is at which point when you spin it? The maximum tension? At the bottom, yeah. At the top, it's the least. Right. That's an external influence. All right. So we need to find the allowed maximum speed at the bottom. I will just label it probably Vmax. Okay, so now let's draw it again one more time quickly. So now we are at the bottom. This is the chord. So again, what we need to find now. Again, what's the name of that velocity which we want to find? Tangential. Okay, now after this, in the third time. Right. So the maximum, this, right, we need to find at the bottom. It's a tangential velocity. Bless you. Right. Coordinate system. Move the coordinate system. So now your object is over here. Freeze the system mentally. Right in position. Tangential direction, radial direction. Right. So this will be tangential direction. This will be radial direction. So now we're going to use these coordinates, these axes. Okay. Yeah. Forces. Tension. Up, right? Along the chord, upward. Tension. And the gravity, of course, downward now. So now these two forces act in the opposite directions. Right? And gravity is mg. Okay, so free body diagram is completed. And the final piece, final stretch. Again, net force in the radial direction equals mass times centripetal acceleration. Universal law, and let's just apply for our case. Tension positive, right? Because now R is upward and gravity is negative. So it's a T. Okay, now since we're going to talk about maximum, I will put the subscript T max minus mg. Yeah, equals to mv max squared over R capital. Okay, so only one unknown, of course, T max. So, yeah.
For that, this centripetal acceleration, are you using velocity at the top, you said?
No. Did I write top? No.
I can't see it from here, I was just,
This is max.
oh, just the maximum velocity.
Yeah, it's here, maximum at the bottom. We're interested at the maximum velocity at the bottom because that's where we expect the tension will be the strongest, and that's where the chord can break.
That's what we're looking for.
Yeah, that's what.
You
That's
gave us T max. We're not looking for T max.
right. T max is given. Right. Yeah, absolutely. So we're interested in this. Okay. So now let's solve it. So V max equals to square root of R over M T max minus mg. So you will plug numbers and you will get what again? Okay, I poorly designed numbers, or maybe not poorly. The answer just now only I realized. It's the same as what we had here at the top, right? So we are spinning it from the very beginning, right, at the verge of breaking the chord. I need to redesign numbers.
Professor?
Yeah.
Wouldn't, if it's at the bottom, wouldn't gravity be in the same direction as the tension? Or wouldn't it be plus mg because it's at the bottom instead of minus mg?
You're saying that mg should be up?
Would be
I-
down. Would be the opposite side.
I'm trying to perfect myself to be closer to God, for example, right? But I'm not there yet, right? I'm still on my way to there, right? To change the rules, right, of nature, so that the gravitational force will be in the opposite direction, right? So no, we assume that the Earth is underneath. And force of gravity is towards the center of the Earth. We cannot change that, right? So every time we assume that the Earth is underneath, right? All the time mg is downward. We cannot change that. But tension, yeah, if the chord is above the object, yeah, it will be up. If the chord is below the object, like in this case, tension is down, right? All the time tension, it's a pulling force. It's not pushing. You cannot push the object with a chord, right? Try to push it. Because you can pull it on. So it's acting on the object, along the chord, away from the object. Okay? Anything else? In the case of gravity, if it's a satellite, instead of tension, you'll have only just one gravitational force, right? Universal law of gravity. Not for example, there's only one universal law of gravity. Okay, there are two additional problems, but I'm not going to look at them. This Atwood machine problem, we discussed it in our recitation classes, right? So, plus it's almost 2.5 hours, it's enough, right? To review. So it's a very, very straightforward, just application of Newton's second law, and occasionally if you need to find some travel time or velocity or position, you can also add kinematic equations.
Fai, 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 fai. Ma tu l'amore sul pianeta te lo fai.